So, hello everyone, my name is Zheyuan Ma, and I am a PhD student at University of Buffalo. So today my topic is about lessons learned from the embedded capture the flag competitions, or the eCTF competitions. So how is eCTF different from other CTFs? So the eCTF is unique in three major ways. First, it focuses on securing embedded systems, which present a new set of challenges and security issues that are not currently covered by traditional online CTFs. Second, unlike the standard attack-only CTF, the eCTF balances offense and defense by including design, build, and attack components. Finally, the eCTF runs over the majority of the spring semester through three phases, allowing time for development and for advanced attacks during the attack phase. And so we have been actively participating in the eCTF competition for many years, and through our many years experience, we have accumulated a lot of insights. So we actually noticed something interesting, and so basically, in the eCTF competition, all teams have the security by design mindset, which means in this competition, the security is a first-class citizen. However, people still fail. They still make a mistake and even make the same mistakes over the time. So naturally, we want to ask a question that what are the challenges that leads to these common mistakes? So what are the challenges in designing a secure microcontroller system? To answer those questions, we conducted a study spanning the 2023 and 24 eCTF competitions. We collected and analyzed all teams' submission, including source code, documentation, firmware, etc. And we also did interviews with individual participants. We asked about different challenges they faced during the competition. So our findings suggest that there are conceptual and practical challenges faced by participants. So for the conceptual challenges, we found that the first one is that the lack of general security concepts. For example, we found that many people don't know how the privilege separation works on an embedded system, and some of them thought the privilege separation is unnecessary, and some assumed that the privilege separation is already there, and they can just develop a user space application on an embedded system. And the second challenge is that when switching from a general purpose system to an embedded system, people are unaware of the difference in the hardware offerings. For example, some teams set the non-executable stack flag to the compiler, but they didn't realize that on an embedded device, there is no program loader or MMU. So no one will honor this compiler setting in the firmware binary. Thus, this non-executable stack setting will simply not work. So the third conceptual challenge is due to the unique threat model. For example, many people didn't consider physical attacks such as side channel or glitching, which is much more feasible on an embedded device. And for the practical challenges, the first one would be the single address space. So in a typical embedded system, everything is directly mapped into a same physical address space, which poses challenges to enforce memory safety and also make the attacks easier. And the second one would be the lack of entropy sources on the embedded system, which pose challenges in designing a secure crypto protocol. And the last one is the adoption of the embedded Rust. Although Rust is famous for memory safety, many of the embedded devices lack the Rust support from the vendor. And the low-level memory access or peripheral interaction can also be challenging when using the unsafe Rust. So currently in our study, we are developing a taxonomy to understand the challenges in securing the microcontroller-based system through the lens of eCTF. If you are interested in our study, I'm happy for a discussion during the happy hour. All right, thank you.
Hey everybody, my name's Will Gibbs. I'm going to be presenting my paper, Operation Mango. So firmware lives in devices that you all use every single day, like routers, NASs, cameras. All these devices are run on firmware. And we've exploited all of these devices. So there's really two types of firmware. The first is blob-based firmware. These are a huge conglomeration of binaries, pieces of code, everything just mangled all together in one huge cohesive blob. And then the other is Linux-based firmware. These are small distributions of Linux like Alpine that run and use individual binaries to run their services. And in these Linux-based firmware, they actually use something called NVRAM to communicate to other services sometimes. This kind of acts like a database, but is very unique to firmware that regular static analysis isn't really apt for handling. And so this isn't just one or two extra binaries for these services, right? This is actually a whole host of binaries, a huge interconnected network, a rat's nest, if you will. So the current state of the art is using symbolic execution to try and propagate these constraints through this NVRAM to find this. But if any of you guys have ever used symbolic execution, it's slow. Kind of sucks a little bit. And so what do you do when something's super slow? You narrow the scope. So instead of working on all of these binaries, they decided to let's just work on a few. Let's deal with all the binaries that handle input from external sources. Or instead of network sources, we'll look at front-end interfaces. We'll look at things that propagate from like admin panels or configs, UIs, what have you. But we thought, instead of trying to limit the scope, if we just had a better static analysis, we can run on all the binaries. We don't need to use symbolic execution, right? So this is where we propose Operation Mango. And to solve that, we created Mango DFA, our value dependency analysis. Really what this is it just shows you the dependency, the data flow of the value as it propagates through different calls. Relatively easy to follow as you execute or taint through the program. We also created rich expressions. Rich expressions, while we're doing our value dependency analysis, retain the history or encapsulate this information as it executes. You can see this name variable goes, and then all the way down through our sprintf, you can see our nice concatenation contains the history that, hey, this came from an fgets, right? Instead of just saying, hey, this was vulnerable at the very end. We also have assumed non-impact. So these next two are our algorithmic improvements that come from intuitions as reverse engineers. So like you and me, when reverse engineering a binary, you come across stuff. You want to get as much out of it as you can. You want to understand the program as well as you can while avoiding the stuff that doesn't really matter. You can see I added 2 extra lines to our code example here. You have this start background task. If you were analyzing this and you come to see this, you see, hey, this doesn't use name. We don't care about this. Let's ignore this, right? But then you get into this say hello function, and you're like, oh, there's this new validate name guy. Let's take a look at that. That's using our name variable that we care about. So that's really it, is avoid the stuff that doesn't matter and include the stuff that does. This actually contributes a lot to speed. Even if it introduces a little bit of inaccuracy, it's still better. And then we also have a coarse-grained sync-to-source analysis. This is a lot of text on the slide for you guys to see, but really the intuition behind it is that when you're looking for a bug, you know where you want to start at. You want to start at system. You want to start at stir copy, wherever you think that the bug is actually going to be at. And then you work your way backwards from there, and you try and see where's our input introduced? What's the highest level that we actually care about? And so what we do is we limit our scope to whatever that highest level is. Instead of trying to start from all tainted inputs, we just go from the bottom, and we figure out where we need to end up. And Operation Mango, our results, we figured out that with this static analysis that we implemented in Anger's RDA, the static analysis module now, available to everybody, we have a 22 times speed up over the current symbolic execution. approaches, we find 3 times more, or bugs in 3 times more binaries, because we're not limiting ourselves to that reduced scope. We have 166 manually verified vulnerabilities, and we also use this in our CEFCOM Project Zero for Pwn2Own 2022-2023, and found bugs in real IoT devices there. Thank you. Operation Mango is available for you guys to look at GitHub. Thank you for everything. Demo. Oh, and demo at 4:30. I'll be there. Thank you.
Today I want to give you a little bit more details. Oh, I didn't time myself, which I knew was going to be a problem. Oh, you're doing it. Thank you. She's great. So I wanted to give you a little bit more details into the AI Cyber Challenge. For those of you that were there for the keynote yesterday, Perry Adams talked to us about the AI Cyber Challenge. I wanted to give you a little bit of inside perspective from one of the competitors' teams. So the qualifications events just finished. The program was announced like a year ago, but we got drips of information over time. And I didn't mention it, but I'm on Team Shellfish. So Shellfish is a large hacking competition. And the winners were kind of, we were dripped information during DEF CON. So the winners were officially announced Sunday. But from Friday to Saturday, this was all the information we had to go on. The information on the left is these achievements unlocked, which was basically a first blood. So whose cyber reasoning system was the first to identify a vulnerability, and whose CRS was the first to patch a vulnerability. Of course, you may think, this is great. I bet these teams were like partying and like really thinking that everything's great. The problem is, scoring had nothing to do with how fast you're able to do anything. So even though we had this information of who was first doing what, we couldn't actually use that in order to understand our score in the competition. So it was all about for every challenge problem. So here there were 5 challenge problems: the Linux kernel, Nginx, SQLite, Jenkins, and Tika, which is a Java program. Each of those challenge problems, every CRS had 4 hours to run and $100 of LLM credit to try to identify as many vulnerabilities as possible. Not only figure out what the vulnerability is, but what commit out of roughly 100 to 200 commits introduced that vulnerability, and then generate a patch that not only fixes the vulnerability, but doesn't impact the functionality. And so the only thing we had was this global view on the right, which again also makes you terrified because you don't know if any team, this is just a global overview of if any team unlocked that information. And so Shellfish was one of the 7 teams to qualify, which was awesome. We still don't know, as you see, this is a alphabetical ordering of teams. We still don't know if we just barely snuck by with 7th or if we should really be happy because we got 1st, but honestly, it doesn't matter. We're happy to be invited to the party. And we should be finding out more information about the exact details of the competition. And so I wanted to talk a little bit about our approach that we took during this competition. So our CRS is called Artificial. That's the logo on the bottom of that slide. And we really base this off of, actually I could even say that a significant chunk of our CRS is open source, although the significant chunk is that foundation without which we have nothing but doesn't do anything by itself. This is a PyData task, which is with Audrey on our team, also known as Relmot. If you know her, she is a core Anger creator and all around just like amazing person. And she created this crazy orchestration framework where you can define different components and define a pipeline of jobs going in and out. The cool thing is you can run this on a 3-node Kubernetes cluster, which was like what we had in the production of the competition, while also running the exact same thing on your local machine using whatever resources were available here. So it's actually, I mean, I thought this was like crazy when the students were telling me about how this system worked. And then as I dug in more and more, I got to understand like, oh, this actually like kind of does work. And then, so because of this, we generated, this is one of our older versions of our pipeline. So we had all these little kind of services that did stuff and took in input. And again, this is another thing that was crazy because you had to work on general C targets, Java-based targets, and the Linux kernel, which all require completely different interaction, different components. So trying to get the data from one part to the other was challenging and difficult to be able to run on all of these. I'm not going to talk about how these individually work because I don't want to give away any of our secret sauce. But I can say at a very high level, the key question everyone wants to know is, were LLMs useful? The answer is yes, but not probably as much as you think. We're not going to get overrun with LLMs taking away our jobs yet. They are very good at certain things. Specifically, we used like a hybrid style approach where we had fuzzing and other types of analyses to try to concretely identify vulnerabilities. But the LLMs were great at patching. That's actually the thing that we found. So super interesting, and I'm getting dragged off the stage, so thank you.